All right, let's talk about friction. If I have a block sitting on a surface and the block has a weight W and is being pushed upon by a force P acting over time at an angle theta, okay, the surface is going to have friction, static, and kinetic. So static means it's not moving, and then we have kinetic, which means it is moving, and we start getting that the bumping, the dragging, and the bumping. Okay, so free body diagram of my little system here would be the block. And the weight of the block is acting through the center, assuming that it is homogeneous and isentropic. And I'm going to say that theta is equal to 0, so we're just going to have our force acting this way. So that means we have the friction, fancy F, acting this way, and the normal force. So this is my friction. This is my normal force. And all normal mean is that it's acting perpendicular to the surface. So over here, my block is acting on a horizontal surface, so perpendicular to that would be vertical, and that's my normal force. Okay. Now friction is going to have different values depending on what's going on. So if I plot my force, P, let's just leave it at P, and my friction, okay, it's going to have a 1-to-1 linear relationship until it reaches this maximum value. And then it gets all bumpy and jumpy and it scoots and acts all weird once it starts moving. Okay, so this is any friction. Okay, and then we have the maximum value, friction max, and that's going to equal to our static friction times the normal force. That's the maximum that we can get. And then once we reach that maximum and it starts getting all jolty and funky, okay, well that's our kinetic friction. All right, that's the moving stuff, and that is not what we're going to mess with in statics class. We're going to stick to nothing is moving, static friction, mu s. Now if we take our surface and we put it on a plane here that we can change the angle on. So here is my block. A K angle phi. So we would then have friction acting right this way against gravity that wants to pull it down. Our friction max remains mu s n. And I apologize, I always draw my mu's funny. I really try, but there we go. And then that means that tangent phi is going to be F max over n, right? My normal force going this way. And F max is equal to mu Sn, n's cancel, which means that the tangent of phi is equal to mu s, okay? So why did I write all this down? Okay, well, at some point, the friction strength, strength being the best word I can think of, is the angle, right, that we can rotate our board here until the block starts moving, okay? And that's our friction value. That's how that's calculated in the lab, if you will. All right, and that comes into play later on when you're doing screws and belts and some other things that you'll see again in dynamics. Okay, let's start with a simple example. We have a 100 kilogram block that is being pushed on by an angle of 40 degrees, 1 kilonewton, and they are acting on a surface. And the coefficient of friction between the surface and the block will be represented by mu s. I want to find the minimum magnitude of coefficient of static friction. So block will not move. All right, so this looks just like the variable one that I drew earlier. So we're going to draw our particle here, because this is just particle equilibrium, right? Because it's all acting on one surface. I've got the weight here, which is 100 kilograms times gravity. I have my force here of 1 kilonewton, or 1,000 newtons at 40 degrees. And then I have the friction force that's pushing against the 1,000 newton load, right? So it's pushing down and to the right. So my friction force needs to push back at it to the left, friction. And then my normal force, which is acting perpendicular to the surface. All right. Summing forces in the y direction. I have the weight, 1,000 kilograms times gravity. That is acting down. I have the vertical component of the force, 1,000 newtons. That's 100 kilograms. Getting excited with my zeros. 100 kilograms times gravity, 1,000 newtons, and it's the vertical component, so that'd be sine of 40 degrees, and then plus my normal force. Remember, gravity, as far as we're concerned in this class, is 9.81 meters per second squared, since we're in metric land, and that yields a normal force of 1,624 newtons. I know, I'm sorry, normal force and newtons, they have the same sign. Okay, now we want the block to not move. So the minimum mu would be the maximum friction, right? Mu s minimum would equal friction maximum. So therefore, my friction force is equal to mu s n. Okay, because we want it just before movement, all right? Which is that funky chart that I put up here. You can have friction at any point, but if we want that maximum value just before movement, where it starts slipping, okay, and scooting along the ground, that's the maximum value mu s n. So that's going to be in the x direction. And I was not good and didn't put up my ordinate system. There we go. Sum forces in the x direction is equal to 0. 0 is equal to, I need the horizontal component, 1,000 newtons cosine of 40 degrees minus friction, which is going to be mu s times my normal force, 1624 newtons. And mu s is what I am solving for. Mu s is equal to 0.472 and it's a coefficient, so it is unitless, and that's the minimum surface roughness I need for friction. I know roughness is different. I apologize. That's the minimum surface friction I need so that I can apply this 1,000 Newton force at 40 degrees and my system not move.